right there. So this is the problem we left off on last time. And so we're going to suppose that 35 milliliters of the 0.180 molarity NaOH solution is titrated with a 0.150 molarity solution of HCl. So in this case, we're taking a base, we're titrating it with a strong acid, right? So we have strong base, strong acid. Let's determine the pH before any HCl is added. So this is just going to be based on that strong base, okay? Notice this is basically the, little pun, the same problem as we looked at before, right? It's just in this case, we're going to be doing things from the base side first, then going up through the same route, and then ending at the acid, okay? Now, the next step we're going to do is determine the pH after 15.75 milliliters of HCl solution is added. Then we're going to determine it after reaching the equivalence point. And then we're going to determine the pH of the solution after 43.25 milliliters of HCl solution is added. So the first thing we need to do here is we need to determine the pH of this base before we add anything. That's part A. So we have a concentration of the strong base right there. Whatever concentration of your strong base, that's your concentration of OH minus that you make in solution, isn't it? And so all we need to do is just 14 minus the negative log of that concentration. And that gives us 13.27. You should always go ahead and double check, does that make any dang sense? Start off with strong base, makes a lot of sense, doesn't it? Okay, the next part we're going to do here is we're going to determine the pH after 15.75 milliliters of HCl solution is added. Now in these problems, you're always going to be doing stoichiometry, aren't you? When you do stoichiometry, what do you normally need to get in? Moles, okay? And so what we're going to get into is we're going to take 35 milliliters, we're going to get that into liters, so divide by 1,000, right? Then we're going to multiply that by the molarity, because molarity is moles over liters, right? And that will give us our moles. Did you guys want to know a little shortcut, by the way, for these? Okay, so this is a shortcut, though sometimes students have difficulties with this. If you do have difficulties with it, just do the normal way where you go into liters, okay? If you take milliliters here, so instead of doing this in liters here, if you took 35 milliliters, over here you're going to get millimolar, because the milli will actually transfer over, okay? Because those prefixes are like saying a scientific notation, aren't they? Okay? And so you can actually save yourself some time. This probably for most of you isn't going to be something that you're going to get really used to, but if you get over into the biochemistry and more advanced stuff, then this is super useful, and that's what most people in those more advanced classes do, okay? They'll actually use this. So again, you could work this problem in millimoles instead of doing it in moles, and in which case you don't have to take the milliliters and get them into liters, okay? And that's a shortcut. It saves you about 4 steps, right? Anyways, you can also work in moles. It doesn't matter. Stoichiometry. Okay, so over here, we again add 15.75 milliliters of HCl solution, and so that is 15.75 divided by 1,000 times the concentration, 0.15, right? And that gives us the moles of HCl. Now, there's 2 ways you could do this at this point. You have 2 mole numbers, one which reacts the other, doesn't it? If you know which way you're going, you could take the large number minus the small number and make sure you understand which is the one you have excess of, right? The other way you could do this is if you really don't know what's going on, subtracting one minus the other, if you end up with a negative number, that tells you which way direction it goes, okay? And so, for example, here we look at these 2 numbers, the moles of NaOH, that's a larger number, isn't it? And so what are we going to have excess of? NaOH, yeah, our strong base. And so we're going to have a base at the end of this. We've gotten rid of some of the base, but we'll have a base at the end. So we take that number of moles of NaOH minus the moles of HCl because it's a 1-to-1 ratio. Everybody understands why this is a 1-to-1 ratio, right? This right here has 1 OH right there. This right here has 1 H, doesn't it? Those are going to combine to make H2O, aren't they? Okay. If this had something like a magnesium and then an OH2, there's 2 of those, that would be stoichiometric equivalent to 2 of them. Yeah, we didn't really leak. No, not much, just a little. Yeah. Yeah, but I'm surprised that it's not that bad compared to what normally is. Yeah. Usually it's, disaster here and disaster here, right? Yeah. Okay. So we take the difference in those moles. That's going to give us the moles of NaOH that remains. We need to then get that into a concentration because we want pH at the end of this. So we're going to take those moles of NaOH. We're going to divide them by the total volume. So the total volume is the 35 milliliters plus the 15.75 milliliters divided by 1,000, right? Once we do that division, that will give us our molarity of NaOH, which is 0.07758. Next thing we need to do is we need the pH. And so we're going to take 14 minus the negative log of that concentration we just got. That will give us the pH. So now we have a pH of 12.89. Notice here that our pH did what? We added acid, so it went down, didn't it? And that makes sense. Again, you always want to double check that because that's how you know I didn't accidentally switch a sign. Okay? All right, so we're going to determine the volume of HCl that's needed to reach the equivalence point. And so at the equivalence point, you have what being equal? The moles of HCl and the moles of NaOH. Exactly. You got it. Perfect. Yeah. HCl being the acid, NaOH being the base in this case. But you're exactly right. I just tackled it a little different. All right. So what we're going to do here is all we need to really do is figure out the take the moles of the NaOH. We figured that out several times actually up here. Remember that? We've done that twice now. Okay. And so we take that moles of the NaOH. Well, we're going to have an equal number of moles of the HCl in this case, aren't we? We're then going to divide, get the number of liters that we would get that from the concentration we were given of the HCl here. Notice that this is actually just M1V1 equals M2V2, isn't it? Remember the M1V1 equals M2V2? Yeah, that's all this is. Okay? We're taking the number of moles we need here, and then we're taking the concentration and bringing it across. Okay, so again, this is just the concentration there. That's the moles of the NaOH, which we need an equal number of moles of the HCl, the acid. We take that and divide it by the concentration. That gives us the volume right there. Now, that volume right there is the number of liters we need to neutralize that solution. By the way, what pH would we be when we're at the equivalence point for a strong acid, strong base? Yeah. So this would be that number of liters of HCl here, and that would give us a pH 7. So let's determine the pH of the solution after 43.25 milliliters of HCl solution is added. So in this case, we need to go ahead and take our HCl and see how much of it we have in excess. There's actually a few ways we can do that. We have right here actually the milliliters or liters that would take to neutralize the doping. Okay? So what we could do is we can do it the way we did before, that previous problem, if you remember that one. We started off with the HCl and put NaOH in it. But we could also do it where we take this volume here and we subtract that off of the volume right there. So it took 42 milliliters to get to neutrality, didn't it? To get to the equivalence. So we have an excess of 1.25 milliliters, don't we? Okay. And so all you need to do is take 1.25 milliliters, get into liters, multiply it by the concentration of the HCl. And that's going to give you the excess moles of HCl. Now, once we have the excess moles of HCl, we need to divide it by the volume, don't we? Okay. And so our total volume is going to be, well, we have 43.25, that was added to 35, wasn't it? Divide that by 1,000 to get in liters. Then we divide our moles by that liters, and we get the molarity of the HCl. Anybody have any questions about this so far? Am I losing anybody? Okay, so once you have this molarity of the HCl that's in excess, all we need to do is, that's an acid, isn't it? That's that strong acid. So we just take the negative log of that number, and that's going to give us the pH, isn't it? There we go. And so the pH is going to be 2.62. Now, does that make sense? Yeah, we have excess strong acid, don't we? It should have a pretty low pH. Okay, so let's start talking about some of the titrations of weak acids and weak bases. Now, I'm going to point something out to catch up on the time that we're missed here and to start catching up on some of the stuff we've had issues with. What we're going to start doing is I'm going to release the Wednesday lecture to everybody, and I'll expect some of you to get some of that. They'll be a bit behind you, and so I'll end up catching past, okay? What will then happen also is every Thursday and Friday, I'm going to release, so your Thursday video they're going to have to cover, their Friday video you'll have to cover over the weekend, okay? And it's basically going to start on 18, okay? Except for this one video lecture to cover this extra 30 minutes that I missed. Yeah. Okay. So now this is going to be a weak acid and weak bases that we're doing titrations on. So again, this is the titration here of a weak acid. Typically what we do is we would take a weak acid, titrate it with a strong base, so we don't get double sigmoidal relationships. Okay? Or we would take a weak base, titrate it with a strong acid, which is the next one we'll cover. Okay, and so here we have a weak acid. Does anybody know how I can determine if this is an acid or base starting? Yeah, the pH at the start, right? Yeah. Okay, and so at A, this is just the weak acid, isn't it? And that's just the equilibrium problem for a weak acid with nothing else added, is it? Okay. This region right here, does anybody know what that region would be? By the way, I'm asking you questions before I've given you the definitions of these things, because I want you to derive it from the stuff you've already seen. This is how you increase your ability to critically think. Okay? So, what would happen in this right here? We're taking that weak acid, we're neutralizing parts of it. When you have a combination of a weak acid and its conjugate base, what do we call that? Another way of thinking about it. Notice how the strong acid, strong base just sort of went up really fast, right? And then went whoosh. This is resisting pH change. Buffer. It's a buffer region, isn't it? Yeah, yeah. It's a buffer, isn't it? Yeah. It's literally a weak acid with its conjugate base. That's the definition of a buffer, isn't it? So guess what you can use in this region? Do we have a formula that makes life easier in this region? We have a Henderson-Hasselbalch formula, don't we? Yeah. And so this region actually becomes pretty easy to deal with because Henderson-Hasselbalch is just a buffer, isn't it? Okay. This region right here, at this region, we've neutralized all of our weak acid, haven't we? This is the equivalence point. This is where your moles of base are equal to your moles of your weak acid. By the way, was there something special about the Henderson-Hasselbalch formula when the moles of base and acid are equal? So in the Henderson-Hasselbalch, Yeah, exactly. Yeah, so remember it's the pH equals pKa plus log of base over acid, right? So if moles of acid and base are equal, that's going to mean we're 1 to 1, aren't we? Okay? When those moles are equal, we will have none of the acid remaining, won't we? Okay? Now, when the moles of the weak acid and the moles of the conjugate base are equal, that would be halfway to the equivalence point, wouldn't it? Okay? What happens when you take the log of 1? That's 0, isn't it? Yeah. And so if that term was 0, pH would equal what? pKa. And so half the equivalence point, what is that pH number there? It's the pKa. See that? Okay. Okay, so this is the equivalence point again. This is the point where we have consumed all of our weak acid with that base. Okay? And at this point right here, this is where we're just adding extra base, isn't it? Okay? Yep, D. So at C, we have consumed all of our weak acid. So this first, when we're putting excess base, we raise up near the pH of the base. And then we hit the point where we get diminishing returns because we're already close. Yeah. Is that like partial drop? Yeah, this would be where you keep adding more and more drops. In fact, these are full milliliters. This region is where you do the partial drops because you're trying to hit exactly C or as close as you can get. And if you do a full drop on this region, you could jump all the way up to here. Like, because this goes up so fast, right? Notice that this region here, this is about 0.5 milliliter, and it goes up about 8 pH units. See that? I didn't see the one. Okay, okay. That's fair. No, that's fair. And this part right here, you're putting full milliliters in, and you get almost no change because you're already almost at the pH of your base. So it just can't raise it much. You're 80, 90% of the concentration already. Okay, so again, our initial pH is going to be higher for our weak acids because they're not going to release as much H plus as our strong acids. The weak acids have a lower Ka values, and they're going to have a higher initial pH values. Again, notice that this starts up at the 2 somethings, right? And if you have a weaker acid, it may start even higher than that, okay? Do you notice something else about this number here, this equivalence point? Is that at pH 7? No. And so weak acids never have equivalence point at pH 7. It's always higher, okay? And that's because the conjugate base of a weak acid is itself a weak base, isn't it? Okay? The conjugate base, quote unquote, of a strong acid is not a base at all, is it? Yeah. It's actually just a negative anion. So the initial rise in pH, the weak acids are going to be port-resisting pH changes until the pH is close to the pKa value. And that's where the buffer gets the best at resisting pH change, isn't it? And so that's where you're entering your really strong buffering system. So the weak acids with higher pKa values are going to have higher initial rises in your pH. And this is this little region that goes like that. See that? You get a little initial higher raise, and then you enter B, and B is where you're in the buffer system. Okay, so the pH at the equivalence point always has to be greater than 7. By definition, because you are a weak base when you neutralize a weak acid, right? It wouldn't have been a weak acid if that wasn't a weak base. So weak acids, these do not release as much H plus as your strong acids. The conjugate bases of weak acids are more basic than the counterions of the strong acids. Again, note that the strong acids are not normally considered conjugate bases because they don't have any basic properties. The titrations of weaker acids are going to have higher pH values at the equivalence point. This actually is reflected by the Kb at that point. That's what determines that number. So the pH change near the equivalence point is going to be less abrupt. The weak acids with lower Ka values are going to have more elongated, less abrupt titration curves. You can actually see this very nicely where we've taken several Kas and put them together. So this is a strong acid. Notice no buffer region. See how that just hockey curves up? Okay. And then it hits the equivalence point region and it just shoots up. See that? Really abrupt change, big difference. Okay. This right here is a weak acid, and we have a Ka of 10 to the negative 4. And because we start at a higher point and then have this buffer region, what ends up happening is the equivalence point ends up higher as well, and that gives a shorter distance here. See that? We don't get this huge raise here. This actually means that titrating very weak acids can be actually quite challenging. Because look at this one, 10 to the negative 8 here for Ka. And so you start at such a high point here, and you end up in this buffer region that's very high pH here. And then what you get is when you're at the equivalence point, there's almost no difference in pHs there. And so it's a very tiny pH difference going from the equivalence point to the base. Okay? And so that can be a little challenging. An equal amount of each of the following weak acids is titrated with 0.1 molarity NaOH. Select the acids with the highest and lowest pH at the equivalence point. Okay, so what's going to have the highest pH at the equivalence point? Or another way of saying this is the strength of an acid is the weakness of its base, right? The weakness of an acid is the strength of its conjugate base, isn't it? Okay? So the weaker the acid, the higher the pH for the equivalence point. Okay? And so that's what we're looking for, isn't it? All right, so which one would be the weakest acid? Remember the pKa relationship to acidity, strength versus weakness? So these numbers right here, this P is negative log, right? So that means the Kas would be 10 to the negative powers, right? Okay. That means the larger this number, the smaller the Ka, right? It is. Got it. So this one right here is the weakest of those acids. That would have the highest pH at the equivalence point. And then this would be your second one in the middle. And then this one right here, that's the lowest pKa. And so that is your strongest acid, isn't it? Okay. You can actually get this from the naming if you're clever about it. Acid, acid, non-acid. Highest number in the pKa, right? Okay. This one's actually typically considered a base in many cases. That's why it doesn't say acid behind it. So pyridinium is normally a base. This is the ion, which has acidic properties now. Anyways, that's the relationship, and there we go. So the initial pH of a weak acid is usually going to be the simplification is going to be possible because less than 5% is going to ionize. And so for this, it's just an ice problem. This is the simplified version of the ice problem. You probably recognize it because we've done it enough times, right? And so, you know, equivalent usually to just saying x squared over the initial concentration of your weak acid, right? And then you would take the pH. This equals the negative log of the H plus. You can go ahead and substitute this in. If you go ahead and substitute one formula into the next, like we do for an ice problem, you'd actually get this relationship right here, which is the negative log of the Ka times the initial concentration of your weak acid. That's equal to the pH. Okay? Do you need to memorize these formulas? Absolutely not, right? You know for a fact, we've done this many times now, right? We can do this with an ice problem, and an equilibrium expression, can't we? It does not take that long. It takes like a minute or half a minute usually. Yeah. So this is just the simplified, quick formula if you want to, if you're good with formulas and you just happen to like that. Okay, so region B, this is actually between the initial pH and your equivalence point. This is where you are entering your buffer region. Okay? And so we can actually use the Henderson-Hasselbalch formula for this region instead. And so in this case, the pH would equal the pKa plus the log of the base divided by the acid. Remember, those are the initial concentrations. Now, do keep in mind that in all these cases with these formulas, we are making the 5% assumption, right? That our H plus, our X numbers, would be less than 5% of our initial concentrations. Okay. So, at the equivalence point, the only thing that's going to remain is your conjugate base. So the pH calculation is going to be the same as the basic salt calculation. So remember where I made you do that calculation for the basic salt? We started with the conjugate base. That's that. That's actually the same calculation you do for the equivalence point. So in this case, we went ahead and substituted those ice tables and equilibrium expressions into each other so that we get a formula that can be quickly done. Okay? And so here's the Kb. The Kb would be the Kw divided by the Ka, right? This would equal x squared, you recognize the x squared, over the A minus concentration. Because remember, we start with the conjugate base in this case. Okay? That's that initial concentration of your base. Okay, so the OH minus concentration would normally be equal to x. If we rearrange this, we would actually get the square root of the Kb times the conjugate base here, which again is that neutralized weak acid, isn't it? We would substitute in the concentration of the OH. We would need to get, for the pH, 14 minus that POH, right? And remember, the POH is the negative log of the OH minus. Okay? So, again, we would just go through and do these calculations just like we always have done. Okay? Just remember, at the equivalence point, you only have the base left. Okay? So you're looking at the conjugate base only. So past the equivalence point, the pH is going to depend on your concentration of the excess OH minus that we add from that excess base. And so that's the major one we have to keep track of and deal with. So the pH is just going to equal 14 minus the negative log of the OH minus that we add from that strong base, right? Now, there are some caveats to these problems. If you get into some weird problem that is very, very small amount, like 1/10 of a drop has been added of the excess base, then you can just do ice problems, okay? If you're ever wondering, how the hell do I deal with these problems? You can never actually be wrong by doing ice problems, okay? Because that's base law assumptions. There's no assumption in an ice problem. It's base law, okay? So again, the ice problems, if you ever go, I'm not sure which region I'm in. I don't know how to do this problem. What should you fall back on? Ice problem. Yep, you can always do the ice problem. You'll always be able to engage. Okay? Ice problem, equilibrium expression, right? These chapters are very nice because you can never actually be completely wrong. As long as you understand the ice problem, the equilibrium expression. May take a while, but you're getting it. I mean, as long as you keep track of your moles and keep your, writings down, keep track of your units, keep track of your signs, right? Then you'll be okay. So suppose that 40 milliliters of 0.5 molarity formic acid, this is the formic acid right here with its Ka, we're going to assume that the X is less than 5% in this case. Solution is titrated with a 0.5 molarity solution of NaOH. Determine the pH at these points. Now, this is actually the most challenging part of these chapters, is the word problems and you understanding the language of the word problems enough to actually set the problem up, okay? Because every problem can be done the same way, ice problem, right? But we have formic acid. Formic acid, according to this Ka, is a what? You got 4 options. Strong acid, strong base, weak acid, weak base. Weak acid. Big hint here being acid. And then this telling you this is a weak acid, isn't it?
Okay, so what about those numbers right there saying weak acid?
The fact that this is not infinite?
Not what?
Infinite.
Oh, okay.
Yeah. Remember that a strong acid would be divided by 0, right? Yeah, you wouldn't have any of the weak acid remaining assembled. Okay? There'd be no acid left. So, anytime you have these numbers like this, and they're not infinite, or 0, literally all the way to 0, then they have to be a weak something.
Yeah. I know this isn't right, but I just thought since that was a smaller number, I just assumed. I know that's not right, but.
Oh, no. The fact that this is a smaller number tells you weak acid.
Oh, okay.
Yeah. The strong acids would approach infinity,
So
meaning large number.
Or
Okay, so in water, this positive exponent for these strong acids ends up going to infinity. But if you start measuring them, remember where we did those weird measurements where I got like actual Ka values for those? Yeah, if you start doing that stuff, the strong acids actually can have positive exponent numbers. But those won't be in water, okay? Yeah, that won't be this sort of conditions. You can actually have weak acids under very specific circumstances where this would be a positive number, but it's going to be something small. Okay? It's not going to be 100,000, a million, that sort of thing. Yeah. Okay, and then NaOH right here, this is the other way you can tell weak acid, strong acid, that sort of thing, is literally just you have 7 strong acids you should memorize, and then you have your strong bases. Those all have OH minus with a metal that's in which groups? Group 1 and the lower part of group 2, right? That's it. If you have those memorized, your interactions with these acid-base problems are much easier. Okay, so again, that's 0.5 for the solution of your strong base, right? So this is really a titration problem that we're looking at with our weak acid and strong. Okay, so let's look at this prior to the addition of the NaOH. So in that case, we have 40 milliliters of that 0.5 molarity formic acid, don't we? And we have a Ka. So you can go ahead and do the relatively easy way to do this, which would be to use the formulaic version. Okay, that is possible. In which case, you would take the negative log of the square root of the Ka value, which is right there, substitute that in, times the concentration of your weak acid, which is 0.5, because we haven't added anything to it. And so we go ahead and do that, 0.5 times that number, take the square root, then take the log of that number. And that's going to give us, well, negative 2.02, because I never said negative part. But after you multiply by negative 1, they'll give you this number. Okay? 2.02. Everybody good with that? Again, I'm doing it the short way to demonstrate these. But if you forget the formulas, I always forgot the formulas. I never memorized those at all. It just is not worth my fucking time because the ice problems were so much easier. Like I could write out the ice problems, derive it in about 20 seconds. And then finish my problem in about 30 seconds. So it just wasn't worth it. If you forget, fall back to the ice problems, right? Fall back to base. Okay, so at half the equivalence point now, so at half the equivalence point again, what is that going to look like? So we're at a buffer region, aren't we? And so that would be the Henderson-Hasselbalch formula. half the equivalence point would mean you have equal amounts of the conjugate base and the acid, isn't it? Okay? And so the Henderson-Hasselbalch has that log of base over acid. If we have the same number in the top and the bottom, what does that give us? 1. Yeah, it doesn't matter what the numbers are, does it? It gives us 1. Okay? The log of 1 is 0. Yeah. And so again, the pH equals the pKa whenever you have half the equivalence point. Okay? There you go. And so we take negative log of the Ka, that gives us the pH. That's 3.74. Everybody okay with that? Okay. This is actually an incredibly important region, by the way. Like, this is one of the most important things about the Henderson-Hasselbalch formula, because it easily allows you to figure out the Kas of acids. In case you're wondering how most of these Ka values were derived, there you go. That's how. Just titrations, just like we showed you in this problem. So at the equivalence point, what is this going to look like at the equivalence point? Well, remember that at the equivalence point, you're going to have all the conjugate base, aren't you? And so what we need to do is we need to take that concentration we're going to need for our conjugate base. That's going to be the 0.5 molarity times the 40 milliliters to get the moles, right? Once we get the moles, we need to divide by the total volume. And so at the equivalence point, our total volume is going to be, well, they're 0.5 versus 0.5, right? So how much of the NaOH do I have to add to neutralize that? Same concentration, so I add the same volume, don't I? Yeah. Yeah, you got it. Yeah. Yeah, so 40 milliliters of the NaOH, and that means my total volume would be 80, right? Exactly. You got it. So we got the moles of our initial weak acid. We divided by the total volume, 80 milliliters. Notice, by the way, if you use milliliters here for both parts, the milliliters cancel. So you can use the same volumes on both parts. You don't have to actually convert them both to liters. Okay? I only did that because people tend to get confused because of the liters here. Okay? Okay, and so this would give us 0.250 moles over liters. That's our concentration of our weak base after we've done this titration to the equivalence point. So the next part I need to do is I need to get a Kb. How do I get a Kb again? I'm going to take the Kw, 10 to the negative 14, divide it by the Ka, don't I? That gives me my Kb. Once I have these two numbers, then I can go ahead and do this several different ways. I could go ahead and do this with a nice problem, of course, or I could use the brand new formulas that Dr. Clausen just gave me. I'm using right here. So again, the POH is going to equal the negative log of the square root of the Kb times the concentration of that weak base. In this case, that being the conjugate base. Did anybody notice that this is the same formula? See that? pH equals negative log square root Ka times the concentration of the weak acid. If you want the POH, it's the negative log square root of Kb times the concentration of the base, isn't it? Yeah, same formula. Because the same reason. It's just deriving, plugging in the ice problem into that equilibrium expression, isn't it? Okay, so we get the POH. We again take that Kb times the concentration we got for that conjugate base, take the square root of that number, take the negative log of that number. That gives us 5.43. We take 14 minus that number of 5.43. That gives us the pH, which is 8.57. We always go, does that make sense? Well, we're at the equivalence point for a weak acid. We have to be a pH that's above what number? 7, exactly. It has to be above 7, doesn't it? So it makes sense. So when the equivalence point has been reached and we've added 2 milliliters of excess NaOH on top of that. So the next thing we're going to do is this is just going to be strong base being added to a solution, isn't it? And we have a fair amount of extra strong base in this case. So we can just go ahead and calculate this as what would be our new concentration for that base. Okay? And so we take the excess that we add, 2 milliliters, times the 0.5 molarity, divided by the total volume. So we got to 80, then we added 2 extra, right? So we're at 82. And so then that gives us a concentration of the OH minus of 0.0122 molarity. When you have the concentration of OH minus, well, you got to take negative log of that and subtract that off of 14, don't you? That gives us pH. And so our pH is 12.09. That makes sense. We just added excess strong base, didn't we? Okay? So our pH is quite a bit larger. This is that very drastic raise off the equivalence point, by the way. That's what we're seeing here. Okay, so the weak base and strong acid titrations, these curves are going to be very similar to your weak acid, strong base titration curves. The only difference is that you start at an initial pH that is basic because you start with base, right? Instead of acidic. The pH at the equivalence point is not acidic, it's going to be basic. It's acidic, not basic. Because again, when you neutralize a weak base, you're going to end with a weak acid, aren't you? Okay. The pH at half the equivalence point is actually going to be equal to the pKa of the conjugate acid of your weak base being titrated. Because again, we're doing everything in pH, we're going to end up in pKa's. Okay? The final pH is going to be acidic, it's not going to be basic, because we'll end up adding excess acid. Okay, so again here, this is that initial equilibrium of your weak base, isn't it? Okay? This region right here, we've added acid to it. Once we've added acid, we're going to take part of that weak base. That's going to be going to, well, the conjugate acid of a weak base is weak acid, right? And so this is that weak acid, weak base pair, meaning this is a buffer, isn't it? Okay? And so this is your buffer region again with a weak base with its conjugate acid. This right here is your equivalence point. In this case, because we're taking that weak base and we're getting it into a weak acid, this equivalence point here is going to be what? It's going to be below pH 7, isn't it? Okay, so we're making the weak acid. And so we'll end up with a pH a bit below 7. Oh, okay. And then this D excess acid, right? We go to the concentration of the acid. Okay, next time we'll start up on this. Everybody have a good day. Actually, you'll end up with a video that will do this. Okay, check out the video, please. Let me know if you have any issues or questions. And you all have a wonderful day.